Okay, so we left off on Friday with a couple problems still to do on partial fractions. So let's go ahead and get started on those, and then we'll see how long that takes us, and then jump into these Riemann sums, trapezoidal rule, midpoint rule, and then hopefully I'll be able to explain kind of the algorithms and how you might be able to code that, or we can get into that in office hours. The other thing I guess we need to talk about, the hardest thing about Riemann sums and trapezoidal rule is going to be the error bounds. That's usually tricky for students. We'll see how you guys do. I know in the math department, a lot of students struggle with that because it's a formula and all these rules are going to be formulas. So one is the skill to be able to recognize a formula and then use a formula, especially for coding and programming, because most of the time you're not going to want to derive all these formulas, and even the error formulas, I don't think any professor knows how to derive them off the top of their heads. Um, so you kind of want to be able to recognize a formula and then know how to use a formula. And sometimes that can be hard if you're unsure of some of the concepts behind it. And then solving those problems. So we'll work those out. Okay, let's go ahead and switch to our camera here. Silva, you say there is one professor that might know how to derive those error bounds. I would believe it. In the applied math department, there might be someone. In the math department, if you ask any of the instructors to derive an error bound formula based on Calc 2, no one's gonna know. All right, so we want to finish up with partial fractions. So a couple of the topics we need to work out. We've seen what happens with just basic factoring. That's where we started with partial fractions. And then we've seen what happens when we can't factor. So certain factors of the denominator will end up being quadratic factors that we cannot factor. And we saw, unfortunately, with those, we do have to use the more formal techniques of finding our coefficients. How did that go for you guys? I know we kind of just threw it in there at the end to check. Does anyone want to see another example like that?
I mean, give or take, it was kind of helpful with some situations, especially when it got up to like the letter E, because then it was a lot more difficult to figure out what X was, cancel what. So it's better to expand it out and do it that way.
And combine your like terms. Yeah. Yeah. We'll see. Let's do a couple of examples. I'm not sure how often it can come up if the numerator is bigger than the denominator. So I do want to at least go over it. And then there's different techniques where we have root multiplicities. And then maybe we'll go over again an example of what happens when we can't use these shorthand tricks, because it is helpful doing these systems of linear equations. And imagine all of you guys are going to have to take linear algebra at some point. It's kind of like getting into a little bit of those skills, solving systems of linear equations. One person had some ridiculous coefficients for a weather sign. Yeah, and that's why, like, if you can do the shorthand trick and pick values of x, it's really nice. It really helps save you some time. Okay, so let's start off with our example of x cubed minus 4x minus 10 over x squared minus x minus 6 dx. And so the first thing we notice with this is that our degree of the numerator is bigger than the degree of the denominator. And that's a problem, right? When we break these things down into our partial fractions, we've cooked them up so that the degree of the numerator is always less than the degree of the denominator, right? Whatever sort of fraction or whatever factor we have in the denominator, we always make the numerator a generic polynomial one less degree than that. And so, well, if the numerators on all of our pieces are all one less degree, we can't add them together and recombine them to get something of a higher degree in the numerator. So what do we do? What's that mean? What do we do when the degree of the numerator is bigger than the degree of the denominator? We have to do polynomial long division. So how's that go? You want to put your denominator on the left, your numerator underneath the radicand. You guys remember doing long division. Let's space this out. All right, let's organize my notes. So we've got x squared minus x minus 6 dividing into x cubed. I'm going to keep a placeholder for x squared here. So there was no x squared. I wanted to make space for that. Minus 4x minus 10. And then you're just comparing the highest degrees. So x squared and x cubed, how many powers of x, or how do you get from x squared to x cubed? You have to multiply it by x. Then you multiply that times your divisor, and we'll get x cubed minus x squared minus 6x. Then you subtract that off. So the x cubes will cancel. We're going to have 1x squared, and then we'll have a positive 6x minus 4x will give us plus 2x. So that's the algorithm. That's our division algorithm. Then we repeat it. So now this is our new numerator, so to speak. And then we can see that we've got x squared going into x squared. And so that's just a factor of 1. Multiply through x squared minus x minus 6. We may want to bring this guy down if it helps you organize. And then we are always subtracting off that guy. So mind the parentheses. It's easy to miss a minus sign if you're not distributing. So when we distribute, we'll have 3x. We'll have plus 6 minus 10, so minus 4. So how do we rewrite our term or our integram? It's going to look like this. Whoops, that should have been a minus here. So whatever the remainder is, you're going to keep doing the division algorithm, and by the mathematical rules and laws of the division algorithm, you can keep doing the division algorithm until the term you're left with is degree 1 less than the denominator. Essentially, that's why we cook up the partial fractions the way we do. And so this will be our new numerator. This term here is our polynomial part. And nicely enough, we can always integrate polynomials. All right, so we rewrite it. I'm not going to rewrite the original integral. Let's just rewrite it with the new form that we came up with. And now we've reduced the problem to something on the order of what we were working on Friday. So what are we going to have? 1/2 x squared plus x plus now our integral of 3x minus 4 over x squared minus x minus 6 dx. So this one, not too hard. I'm going to say finish on your own if you want. You can see the denominator is going to factor nice. X minus 3 times x minus x plus 2. So coming up with those coefficients will be really easy. Practice that. You should be able to use the trick, pick nice values of x equals 3, x equals -2, and finding the coefficient should be really easy for that. And then the integrals should be also really easy because it'll be like a constant over x minus 3 and a constant over x plus 2. So you should get easy natural logs for the integrals. I don't want to finish that because I want to see if we can do some of these harder examples, especially with irreducible factors. So that was just long division. Any questions on that? It's kind of the only example I want to do of long division. It should be review, but I know like it's just a process of calculus. You learn polynomial long division like once in pre-calc, and then you don't use it again for like a few years until maybe you get to this. And then even after this, calc 3, you'll never use it again. So it's always one of those things that you kind of review once, have to use it a little bit, and then you'll forget it until you need to use it the next time. At least when you're young and doing your undergrad, because you got so much other things to learn. Okay, so let's take a look at our another example, and we want to take a look at root multiplicities. And let's do something like, let's see, we got 3x plus 4 over, sorry, I'm getting a little off screen, x plus 1 times x minus 2, and let's say cubed. There's actually two different ways to do this, so I kind of want to go through both. Excuse me. So what do we want to do? We want to first break down our partial fractions. And let's do this kind of default way of the way we set this up, where we just blind rule of we split it amongst the factors of the denominator, and then the numerators are degree 1 less than the denominator. And sorry, this was a cubed here. So the first factor is easy, just a linear factor. And then the second factor is a degree, it's a linear factor, but it's cubed. So it's a degree 3. So what we can do is just put a generic degree 2 polynomial over that. And then now we go through the same methods and we try to find our coefficients. So we're going to have a times x minus 2 cubed plus this bx squared plus cx plus d times x plus 1. That would be the numerator if we combine those. And of course, we got to equate it to the other numerator. And we can use a little bit of tricks here, picking nice values of x. Again, since we have linear factors, we can check x equals -1, and that'll give us a times -3 cubed. So this whole term vanishes, and so we will have -27a is equal to, what was that, just 1? And so our a is -1/27. Not the nicest of factors, but we'll have to get through it. And then how do we find the other ones? We can check x equals 2. So that'll kill the first term. And then we'll have b times 4 plus 2c plus d, all of that times 3 is equal to the right. So what do we get? We will have 12b plus 6c plus 3d equals 6 plus 4 is 10. And so what happened with that? Well, we got something. We have an equation that should be valid. But because we had to use 3 different variables in the numerator, and we only had one nice choice of x for that whole term, well, I can't solve for 3 variables with only one equation. So what do we need? We need more equations. Couldn't we do x equals 0? Yeah. So there's a lot of different things we can do. We can go back to, we can do it the traditional method where we expand everything out and combine like terms. Or someone's looking ahead, someone's being pretty clever and saying, hey, couldn't we do x equals 0? That would at least cancel out some of the terms. And that's the other thing you can do. So as I mentioned, this technique of choosing x values is just, it's kind of a slick technique to recognize how we can reduce and get rid of some of the variables. But the biggest principle is the fact that when I have an equation of polynomials, two polynomials have to be equal for every single value of x. So in this attempt of choosing values for x, well, we have all these extra variables. We need extra equations. How do we get extra equations? Plug in different values of x. So we have one equation. If we can find 2 other values of x that are nice and easy enough to compute, it'll give us 2 more equations, and then we can solve those. The other thing we could do, as I said, is expand all of these out and equate term by term to come up with the coefficients. So in that case, why would we maybe not want to go that route with what we have?
It'll take too long. It'll take too long, and it'll probably get a lot more complicated and room for error.
Yeah. So good. It's kind of like meta problem solving techniques to take a look. To combine like terms, we're going to have to cube this guy out, FOIL this guy out, which we can do, right, as Calc 2 students. But there might be some error and it might take a little longer. We already have a, we know that, and we only need 3 more with one equation. And as someone mentioned, if we pick x equals 0, it'll at least cancel our b and c terms. So x equals 0 is another value to compute, especially because it's an easy thing to compute out and give us an extra equation. So let's go ahead and do that. And so x equals 0, I'm going to keep a as a. We'll plug in -1/27 at the end. -1/27 is just a harder number to write and organize in terms of our work. So I'm just going to keep a as a and know that we know it already. So when we plug in x equals 0, we'll get -8a plus our B and C term are going to be 0 plus D times 1 is equal to 4. So that gives us a pretty easy equation relating A and D. And since we know A, of course, we can solve for D. So what's that reduce to? We get D is equal to 4 plus 8A. So 4 plus negative 8 over 27. Not the nicest of denominators. What's 4 over 27? 108. Someone check that math for me. Got it? Good. Cool. So now we have 2 of our variables. We need to get B and C. So we need at least one more equation. We can still use this one here. And then what do we want to do? We're going to want to pick probably another value of X. Again, that would be the easiest. And so if nothing pops out at you, right? We tried 0. That was nice because it killed some things. Of course, we tried 2. We got negative 1. The other one that might be easiest is just pick a small value that's easy to compute, right? So let's go ahead and pick X equals 1. So there we will have A times negative 1 cubed plus B plus C plus D times 2 equals 3 plus 4. So a negative A plus 2B plus 2C plus 2D equals 7. And now we get the joy of computing all that. So let's go ahead and do our fractions here. So A was negative 1/27th, right? Yeah. So I'll have 1 over 27 plus 2B plus 2C plus 200 over 27. Let's go ahead and find our common denominator of 27. So 7 is what, 140 and 49. So 189. So we'll have 201 minus 189 is 22. Yeah. No. 12. Yeah. 12 over 27. And so this we can use as our second equation. Let's go ahead and rewrite our first one as well. And we might want to simplify it. So we've got, those numbers don't look good. 12B plus 6C plus 3D equals 10. Let's go ahead and work with number 1 and reduce it down to B and C. We've got 12B plus 6C. 3D, D was what, 100 over 27? Equals 270 over 27. 12B plus 6C Subtract that off and we get negative 30 over 27. And that reminds me, we forgot this negative here, right? We'd have 201, so 189 minus 201, we should have negative 12. Here we had 270 minus 300, negative 30. Okay, so we've got two equations. Let's keep reducing them. Is this all making sense to you guys? I guess I haven't like formally set up any sort of process, but this is how you work now with linear equations. This is usually what I do whenever you have a system of linear equations. I like to write them as numbers and put a circle next to them, and then just to kind of like notate to myself, when you're making a substitution into one or the other, or what operations you're doing on them. So I'll show you here in a second when we actually need to work with the two equations at the same time. Right now, I'm just simplifying each individual equation. Of course, if we wanted to go back and label our A and D equations, A equals 27 as a equation 3, D is equal to 100 over 27, equation 4. We're, of course, substituting those values into these equations and now reducing them. Let's go ahead and reduce our coefficients for both of these. So this one, right, I have 2b plus 2c equals negative 12 over 27. Let's divide everything by 2. So we'll just get b plus c is negative 6 over 27. Here, it looks like we can divide everything by 6. So 2b plus c is negative 5 over 27. And those reduce the numbers quite a bit for us, especially since we got these fractions. Hasn't actually been too bad. Nicely enough, when we do the additions and subtractions, the numbers have stayed within a reasonable range for mental computation. And so now we've got our two equations reduced. Let's go ahead and look. Let me rewrite them. I like to put them on top of each other, and it's a nice way of looking at it, especially once you get to linear algebra. This is going to correlate to what's called row reduction operations. And so one of the techniques we've already done is substitution. That's some of the basics where we solved for A, of course, substitute that into the other equations. Solve for D, substituted that into our equation 1 and simplify. We could continue using that method if we wanted to. We could take either of these equations. We could say solve equation 1 for C and then plug that equation into number 2. Go ahead and then you'll solve out for B, substitute it back in. The other techniques you can do, hopefully you've learned somewhere in high school or in college already, where we can perform linear operations on the equations themselves, meaning we can add, subtract, and add and subtract times scalar multiples. And if we notice, we already have c's in this equation, and they have the same coefficient. It's nice when that happens. So what we're going to do is take equation 1 and then subtract off equation 2. So that's how I notate it. That's why I like to put circles around there. And since we're subtracting off the equations, as objects of equations, what are we going to get? So I like to put a colon there. On the left-hand side of the equation, we've got equation 1 minus equation 2. We'll just be left with B. The C's will go away, nicely enough. And then on the right-hand side of the equation, we've got the right hand minus the right. So that's essentially all you're doing when you're subtracting and performing linear operations on equations. See what happens to the left sides, see what happens to the right sides, and then keep your equation, your equal sign where it is. So we'll have minus 5 minus a negative 6. So that'll just give us 1 over 27. And you can see how nice that was. It was a little bit quicker than if I had to solve this one for C and then substitute it in. A little bit more work that way. And then, of course, now that we got our our B, we can find our C by plugging that B back into one of these two, whichever one looks simpler. And it looks like 2 is going to be easy enough for that. So I usually put something like a double equals with an arrow to say I'm sticking this into, let's say, equation 2. Or you can put like a hook arrow if you want. So substitute that. That's kind of my symbol for substituting that into this equation. So we're going to have 1 over 27 plus c equals negative 6 over 27. And so c is negative 7 over 27. And as you guys were saying in the comments, yes, and we haven't started the integral. Yeah, so this one was lengthy. It sounds like from your guys' WebAssign, you guys have WebAssign ones that were this long. Some people were saying earlier in the chat, I think, that take forever. Yeah, this is the problem with systems of linear equations. When you get good at it, you can go a lot quicker. I wanted to take the time to do all the steps carefully to make sure all you guys are following, especially with these kind of parts. The constants, it's the pain, right? It's the hardest part of these, working with all these systems of equations, plugging in, getting values. But now that we have them all, we can do the integral. And then we run into a problem. I almost don't want to do the integral for the sake of time. What time is it? We've got plenty of time left in the course. Let's take a look at what we get now. So if we see our notes, that was our box for this subset of work. This is going to be the close of the box for that subset of work. Finding the constants. And now we've got to get back to the actual integral. So we've got, I'm just going to write it out as our integral of a over x plus 1. Sorry, off the page there. Dx plus our integral of bx squared plus cx plus d all over x minus 2 cubed. So if you get messy numbers like this, so sorry, I didn't previously work this up. I think these are usually a lot of the problems that I'll steal from the book or a book somewhere. And if the constants don't work out nicely, keep the constants as constants. Hopefully you guys are getting the hang of integrals. You know how to work with constants and integrals, and you're a little bit better at abstract thinking. So I don't want to write the denominators of something over 27 with all these. Keep them as constants if you want and do the integral. So this one's going to be a natural log of x plus 1. Easy enough. How do we do this integral?
Can you split it up so then you have bx squared plus, or like the integral of cx and the integral of d?
Yeah, that's pretty much what you're going to have to do. And it might be tricky. That middle term, we're probably not going to be able to do very easily. Let's take a look. So we've got the integral of bx squared over x minus 2 cubed plus cx over x minus 2 cubed plus d over x minus 2 cubed. And let's go through the techniques. So I don't want to go through all of these because I actually want to show you a different way of doing these types of problems to see if it will be a little bit quicker. We'll probably get something similar, but there are easier ways to do it, especially when we get something like this. So how do we do this one? If we were to just try to do that problem. Anyone know the integration technique? U sub, yeah. So this one, we can expand the denominator and then do a u sub. It might work, though the u sub might not, because there's a linear term in the u sub, it may not work. So you have to do some tricks. This one, we can just integrate. This one might be a little difficult though as well. I guess all of these you could probably do a linear u sub, which wouldn't be too hard. What about this one? What would you guys do for that?
Can you set u as x minus 2 and then solve for x by itself? So then you can plug it back in.
Yeah, that's what I was just saying. So that one's probably not recommended this way here. You could do u is equal to x minus 2. So this is just a basic linear substitution. And then du is, of course, dx. Then the trick with these is that you get x is u minus u plus 2. And so when you do these substitutions, you'll get the integral of b times u plus 2 is how you have to substitute out this x in the numerator, u plus 2 squared, and then over u. And now this one, you would have to FOIL that out and complete it. Same thing with this one here. You would have to do something similar. C times that u plus 2 over u.
Wouldn't that bottom u be u cubed?
Yeah, excuse me. You would have to FOIL it out and, of course, then expand each of these terms in the numerator over the denominator plus d over u cubed. And again, that one we can integrate. So this one's getting lengthy. I'll leave it to you guys to check, to go through that, all that work, if you want to check that. I want to go over one more technique of how to do these integrals. And the technique it's similar to if we were given something like this. There's some fancy sort of quick and slick ways you can make substitutions for these x's to simplify things a little bit more. It is kind of similar to the vein of doing this u sub, but doing all of that algebra would essentially get us to a technique we could have started with, which might make our lives quite a bit easier, and what happens with root multiplicities. So let me see, where was our original problem? Let's go back. All right, you guys with me? Anyone need a break? Take a short refresher. That was a lot we just did with all of these. Yeah, please be a short. This is a shortcut method. It's going to be a lot easier. That's why I wanted to stop that. We kept going, and I kind of just saw it getting more and more difficult. I'm like, I don't want to do this anymore because there's an easier way. So everyone kind of flush your brain for a second and kind of get that out. I know sometimes you get bogged down in the calculations and you want to just kind of, sometimes you keep going and going. And sometimes your brain just needs a break now to reset and see, let's get back to our bigger picture, where we started, what we're looking at in terms of the math we're trying to do. Here's the easier way. When you have root multiplicities. So the first one's still going to be the same, a over x plus 1. Now, the second one, and someone said they gave up on that one. Yeah, that was basically number 10. So someone had this, you guys had something like this in the WebAssign. Was the WebAssign due Friday or over the weekend?
It was the one due on Sunday. It was just an absolute mess. So this kept getting worse and worse the more you integrated it.
Bummer. Well, because I'm wondering now, I almost wish we could have gotten to this on Friday. I don't know if it would have helped, because instead of doing it with this degree 1 less than the denominator, as we saw how messy it got, when there's root multiplicities, we can actually do a fancy trick and just say, well, we should have b over x minus 2 plus c over x minus 2 squared plus d over x minus 2 cubed. So think about that for a second. Like, well, one, look at it, see how much easier it is. We already found our A, B, and C and D. Actually, sorry, these are different A, B, and C's. And the A will be the same. Let's call these B's different. Let's call this B prime, C prime, and D prime. They're going to be different. But why is this philosophically the same thing? So for one, we recognize at least these integrals are easier. They're all constants. What are the numerators? We have always degree 1 less than the denominator. This is kind of what we want to do in terms of our theories of partial fractions, right? The degrees of the numerator should always be 1 less than the degree of the denominator. And by the fundamental theorem of algebra, every polynomial is factored either into linear or quadratic terms, which means we shouldn't really have to work with anything bigger than a degree 1 than linear terms in our numerator, which is why this previous one got messy. We started to have to work with quadratic terms in the numerator. And it's doable, as we see, like, each of these are doable with some u subs. It's just lengthy in computations. This, not so lengthy in terms of doing these integrals, right? I can integrate that. We can integrate that. That's just a constant times x minus 2 to the negative 2. Another easy integral, another easy integral. Why is it philosophically the same? So let's just think about it. Let's see. My same concept. In terms of how we're breaking down these fractions. Anyone see it? Of course, the trick is, well, what would happen if we tried to find a common denominator? On the right, of course. Well, what are we going to get? We want to solve for these constants, so let's write it out traditionally, like, or how we've done in all the past ones. We're going to have an A. What is the common denominator? I know a lot of people can't get in the habits, especially pre-calc students and some calc 1 students, right? When we want to find common denominators, some people multiply all the denominators together. That's one thing you can do. But of course, if our denominators are the same factor, just with different multiplicities, our common denominator is going to be the one we started with. It's just going to be the individual factors with the highest multiplicities. So A, of course, we're still just multiplying by x minus 2 cubed over itself. Our new b prime, what are we going to have to multiply this guy by in order to find a common denominator? I need that x plus 1. And then we're going to need 2 factors of x plus 2, or of x minus 2. C prime, we're going to need x plus 1 and 1 factor of x minus 2. And then our d, so forgive me for running out of space here. I'll write it below. We'll need just that factor of x plus 1. So what's different? Um, well, we're finding a common denominator, and we have these extra factors of x plus 1. But in the previous example, we just had a quadratic term over this x minus 2 cubed. And so if we were kind of just looking like we want to combine these three, it'd be like adding these three terms, except what wouldn't we have? We wouldn't need the x plus 1 if we were just finding a common denominator for those three. And what would result if we combined all those terms, expanded everything out? What degree of a polynomial would we have? We'd have a degree 2 polynomial plus some linear terms and, of course, constant terms. So you could theoretically start from here, combine only these three in a common denominator, expand everything out in the numerator, and you'll end up with another generic polynomial of degree 2 in the numerator divided by x minus 2 cubed. You would essentially be going back to this situation. And this is what I was trying to say with this part. There's ways you can go from this and make some nice substitutions for x and getting an equation like this. But it's easier to just start with this. Okay, so let's see how much time we got. Let's go ahead and try to work this out. Let's work at least part of it out to see if it works any quicker for us. And then maybe I'll probably just leave the integrals to you guys. The integral's easy. So we've got a times x minus 2 cubed plus our b prime x plus 1 x minus 2 squared plus c prime x plus 1 x minus 2 plus d prime x plus 1 is equal to 3x plus 4. And now we can do our same trick. So what's going to happen with x equal to negative 1? It's going to kill that term, and that term, and we should get the same a value. Since that a constant was over the same denominator. And now when we choose x is equal to negative 2, positive 2, excuse me, it's going to kill a, b, c, and now we get d prime basically for free. So we got two of the constants for free. And then now, how do we find b prime and c prime? So again, we would want to pick easy values for x that we can compute. So now the difficulty is, unfortunately, we don't have like x equals 0. We can still compute it, but it's not going to kill off my a or d terms. So say we want to do x equals 0, and then maybe you want to do like x equals 1 again. Similar to how we did in the last one. So go through that if you want. It might be a little lengthy in terms of solving those. But again, since we have our a and d, unfortunately, the fractions, they didn't work out too nicely. So I don't want to go through the computations in this example. I think the hardest thing in this example was the cube. So I didn't want to I think the cube just made things extra lengthy because it gave us that extra variable and just a lot more computations to do. Hopefully none of these are much more than a degree 2 term. And then now doing the integral, I guess that we can do in terms of our constants. And the integrals are easy. We got a natural log of x plus 1. That one, b prime, natural log of x minus 2. Sorry, I forgot my constant a there. Plus c prime times, what's our antiderivative of 1 over x minus 2 squared? X minus 2 to the negative 1. Of course, we'll need a negative 1 here. And then we'll have a negative 1 with this guy. Actually, hang on one second. What's our constant going to be here? Plus d prime. Here we'll have x minus 2 to the minus 2. And so we'll need a negative 1/2. All right. Any questions on that guy? So sorry for that guy getting a little lengthy. I actually changed it a little bit, and I think I threw in the cubed because I did want to emphasize just kind of how that works. But nicely enough, if the factors are of different powers, you can essentially put your generic polynomials as just constants and then increase the powers. It can get even trickier if you have terms that are irreducible. So maybe I don't want to go through an example because I do want to get on to approximate integration. It can get a little trickier. Let's maybe try to cook up something easy. If we have something like, I don't know, 2x plus 1 over, let's pick an irreducible quadratic and then raise the degree. So when we have something like x squared plus 2x plus 1 dx, that's not what I want, plus 2. So check your discriminant. B squared minus 4ac is going to be negative. So if this is irreducible, how do you split it in the partial fractions? You would do, oh, and we want to put a multiplicity here. Let's put a multiplicity of 2. So pain in the butt, really complicated. What you can do is keep your irreducible factors similar to how we set up the last problem, but now put 1 with a degree 1, but the polynomial up top has to be a linear term. And we can put x squared plus 2x plus 2. Now this term squared, but the polynomial up top, again, has to be a linear term. Sorry, cx plus d. And as you can see, that one would get extra lengthy because now we don't even have numbers we can plug in nicely. We would have to use a lot of linear operations to find our A, B, C, and D from the get-go, and then integrating these individually can be pretty difficult. But that's the general idea. Does that make sense of how, like, when there's root multiplicities, you can essentially just keep those different multiplicities as separate denominators. So degree 1 of whatever that factor was plus now the next denominator is of degree 2. And then now, since these were quadratic, you've got linear in each of the numerators. In our previous one, we had a degree 1 root with a multiplicity of 3. So we have, here's degree 1, degree 2, and degree 3. And now all the factors can be linear. So degree 1 less than the irreducible factor. Okay, so that was a lot of computation with these guys, as it sounds like they can get into, especially with the WebAssign problems you guys have worked on. So hopefully that was a little illuminating. Hopefully you kind of saw some different techniques. This is a big part of Calc 2, with just being able to think through different techniques and try to sort of think ahead a few steps to try to see which technique might be easiest, whether it's a technique of integration, techniques of splitting different partial fractions. We'll have a lot of this coming up this semester. And if you guys have to continue, differential equations is very similar in this vein. I consider differential equations, it's kind of like Calc 2 on crack, because now you're taking second order differential equations and trying to integrate them twice. And it's a grab bag of tricks that you kind of just gotta know all the tricks and then be able to see the problem, think through which tricks might be helpful, recognize forms of problems, forms of equations, forms of things we want to integrate, and be able to think and kind of pull the technique out of your bag of tricks that you kind of keep stored in your brain. So this is kind of the difficulty of Calc 2. It's not as easy as Calc 1, which can be formulaic. If you have to take a derivative, there's a product, use the product rule. Quotient, use the quotient rule, right? Integration, it's like grab bag of tricks. When you see something, which one do I choose? And so some of the biggest problem with Calc 2 is just doing enough problems where you can start to see things and do things a little more quicker without going down a rabbit hole that's going to lead you nowhere. Any questions?
Yeah, with that last problem there right at the end, it looks like it's breaking the equation up into two separate things to integrate just adds more complexity because you're left with two linears over just more stuff.
Yeah. Well, like this one we can't. Well, I guess we can, right? This one we could have just straight up used a U sub. I was just thinking of this problem off the top of my head and not thinking whether or not it was doable. This one you might be able to do a U sub and shift these guys around to make it work. This one, once you find A and B, you could almost for sure do a U sub with that one. But yeah, whether it makes it easier or difficult, it's kind of debatable. The problem with a U sub light, if we sub out our denominator, we would have 2x plus 2 in our differential, which we can then factor out the 2 to get an x plus 1. And so the differential doesn't quite match up with the numerator. So you'd have to do some fancy manipulation to get it to match up, which you can do. And then you might end up with like a constant term over this guy. And if we had a constant over a quadratic, like if this was just b over x squared plus 2x plus 2, which we might want to separate out in terms of doing that integral, we'd have to do a trig sub. And how would we do the trig sub? Well, we'd have to complete the square in the denominator. So no matter which way you approach it, it's going to get hairy with something like that. And I don't know how many of these problems we would give you anything like this. I don't know if it's anything you guys would see because it does get really hairy. I just wanted to illustrate the technique of like how it would theoretically be broken down, namely this concept of whatever the irreducible factor is, even if it has a multiplicity, this is how you could theoretically set up your numerators in terms of your partial fractions, in terms of solving those. Other questions? All right, let's take a break real quick. Then we'll get back, we'll do some approximate integration. Okay, so let's get back to it. Hopefully everyone had a little bit of a break, flush your brains a little bit. As some people were mentioning in the chat, doing homework with these lengthy problems, it can be a grind 24/7. It is important to take breaks though, even if it's for 5 minutes. I don't know how much meditation practice you guys do. I try to keep up with it. It's another thing that sometimes it just feels like work. And when meditation feels like work, that's when you like really need it. That's when you should really take a break and just try to flush your brain. I think studies have shown where, when you're learning something, the most optimal way to learn something is to take short but frequent breaks, especially in math when you're trying to do something that is somewhat creative, right? It's both very technical and a grind and analytical when you're doing these partial fractions, just computing. But then when you're looking for these techniques of integration, trying to see bigger picture things, broader concepts, it gets a lot of you got to have some creative juices going, some insight, some deeper insight. And that doesn't come to you when you're in a grind. Like a lot of people will say sometimes you have your best ideas in the shower or right before you're laying to bed. That's when your brain can unwind and you can access these different brain states where you can get these creative juices flowing. And it's important for math. So taking these breaks while you're grinding and try to just turn off electronics, keep those away out of vision. You don't want to be staring at a computer screen. That puts you in that type A. I think the alpha state is what they call it, the alpha brain waves. And then that's the computational state. So turning off all your electronics, trying to clear your brain, do some breathing techniques, or go outside, go for a walk, something. And then when you come back and reapproach it, it kind of refreshes your brain. Hopefully then you can see your mistakes more, especially if it's like a test or quiz. I know tests and quizzes, it's hard because you got to stay there to take the test and quiz, but at least, cover your eyes, look away. Just, I encourage my students to do that after they're done. Close your eyes and space out for 5 minutes and then relook over your problems to find your errors. It's a good way to help you refresh your brain, and you'll be able to see the errors you make. Whereas sometimes when your brain's in that mode with the error you made, when you look over the problem again, your brain still follows the same line of thinking and you won't catch it. Okay, so let's get into something a little easier for now. It is still heavy computationally, but I think the concepts are much easier. So let's go back to our document camera here. And we want to get into approximate integration. So this is section 6.5. This seems a little out of focus. Let me see if we can write a little more and get that focused. So it sounds like most of you guys have seen right hand and left hand rule. So really what we want to get into is the trapezoid and midpoint rule. Let's do a little bit of just abstract of what's going on. Oftentimes we have functions that we can't integrate. We've already seen a few examples that are at least really difficult to integrate. And of course, you can imagine we can cook up even harder examples of functions where no techniques of integration apply. Or more practically, what happens is we don't even have functions. We oftentimes just have a set of values where we want to approximate areas under the curve. So we usually have some start value, some end value. And what we want to do is to divide up the interval in question into some specified number of parts. So we divide into n intervals, dividing our one interval into smaller intervals. Of course, the size of the interval is going to be the length of the interval divided by the number of partitions that we take. So it's another word we use, these divisions, we call these partitions. And we call this our delta x. So of course, this is our x-axis. Delta x, this is our change in x of how we're stepping through each value. We want to find f of x for each x in the partition. So our x, we are now going to use subscripts because we're going to index them. So we have our x0 is our starting value. Our x1, so this guy's going to be x0. We'll have x1, x2, x3. They're going to keep going up, and our b is xn. And of course, that one will be n minus 1, xn minus 2. So what is x1 going to be? It's going to be a, and then we just move over by delta x. And so a plus b minus a over n. Actually, I'm just going to keep it. Let's keep it as a plus delta x. Usually you compute your delta x, and if you were to write a program, you would keep it like that. And so of course then our x2 is a plus 2 times delta x. It's going to keep going and going. So for a given index, a plus I times delta x. And you can keep going and find that our xn will end up being b. And so then the other one we want to compute is our f values. So we're going to compute f of x0, f of x1, all the way up to f of xn. So this is kind of the algorithm, the process. Pictorially, geometrically, what we're doing, we're finding this value, this value, this value. All these values are the f values at the corresponding x values. And then we can, actually, sorry, let me not draw the lines there. From those values, let me actually make those darker. I'll put those in black. From those values, we can then do different types of sums. Let me see if I can draw this. It might get a little hairy I almost want to use the same graph, but with different colors, but I don't know if that'll be visual. So maybe we'll draw a couple pictures. So let's correlate stuff. So I like to make a table. For these problems, if you're coding it, you can probably have the code spit out the table for you, which would look real nice. And then, of course, it would compute the antiderivatives for you. But what we're going to have now is our table of x values and f of x values. So the first x value is a, of course, which was x0. Then you've got your x1, your x2, all the way up to xn. You're computing the y values that correspond to those. And then now we want to use those to compute and estimate our areas. So the ones you should know are the left and right hand rolls. So let's go over the left right hand rule, and let's do trapezoid rule first. Those are the easiest. Midpoint rule is technically more accurate in terms of the error, but it's kind of a pain in order. You have to recompute things sometimes. And it looks like we're about out of time. So just real quick, let's go over it, how this is done. So our left-hand rule, we are using the left hand as our height. So the first dot is going to be our height. We're drawing a box. And we draw a box over to the next partition. So you can see how each of these boxes are touching the left. We would then compute the areas of each box, add them all up, and that gives us an approximation to the integral. If we wanted to do the right-hand rule, we use the right-hand side of each interval. I like to start at the second one and then draw the boxes to the left. And so you can see sometimes the left is an under approximation while the right is an over, and sometimes they'll flip depending on the concavity and direction. Corresponding to the graph, what's that going to mean? Or excuse me, to our table. Our left-hand approximation, we're going to use all of them up to here. Let's squeeze in one here. Xn minus 1, f of xn minus 1. So you're going to use all of the values except the last one. For the left-hand approximation, use all of the values except the first one for the right approximation. And we'll write down the formulas in our next lecture of where those come from. And then what we're going to see is we're actually going to sort of combine these into trapezoids to give us a trapezoid approximation, which will actually just be an average of the right and left-hand approximations. Any questions? All right. So I'll see you guys tomorrow. Sorry for going a couple minutes over. Stick around if you have any questions. We'll have office hours tonight, 3 to 5.